Yeah, so welcome to the Geometry and Model Theory Seminar, summer edition. Today's speaker is from Strasbourg, Daniel Panzzolo, and he will tell us about the resolution of singularities of differential operators in dimension 2.
Okay, so first of all, thank you very much for the invitation to the seminar. So for those.
Oh, sorry, Daniel. I need to unmute you for some reason.
Can you hear me?
Yes, now it's good. Sorry.
Yeah. Some people perhaps have heard this talk in the Zagreb's seminar, so I'm sorry, it will be quite similar. So, I hope it will be understandable because I just try to be very basic. So, yeah, so the basic problem that we can put is to solve differential equations. So here I make a small introduction about, let's say, ordinary differential operators versus partial differential operators. So in the more general form, you can imagine this as a polynomial in a function and its derivatives. And this function can, of course, depend on several variables. And you want to solve such a kind of equation. And of course, the basic thing that you want to answer, first of all, is the existence. So we have some very general results for the existence in the case of ordinary differential operators. It's the Cauchy-Lipschitz theorem. And then in the case of partial differential equations, we have more or less general result is the Cauchy-Kovalevsky. I'll come back to this in a moment.
Daniel, P means a polynomial or just any function?
Yeah, it's any function for the moment, but I will particularize to the case of polynomials. And in my case, in fact, I will treat linear differential operators. So here I have to suppose that P is linear in F and these derivatives. But of course, for the moment, it's just a general discussion, and I would. Yeah, that's the meaning of solution, and of course, instead of solving the equation explicitly, you can also try to understand its qualitative behavior in the sense of Poincaré. So it's okay. Let's see. It's and okay, some basic, let's say, question is how to simplify when you are in face of a very complicated differential equation. You want somehow to simplify it to fall in a simpler case. And the matter is that singular differential operators appear very naturally. So just a simple example related to the actuality. So here, the SIR model for epidemiology, you see that even if you write the simple differential equations, you find yourself with a singular point here, and interesting things happen near the singular point. So this is an ordinary differential operator. An example of a singular partial differential operator, it's a very classic example of the Laplace equation when you try to solve it on open manifolds. So more generally, I'm talking about Laplace equation on manifolds. This is, in fact, the Laplace-Beltrami operator. And in this case, to write the Laplacian, you need to have a metric on your manifold. And if your manifold is open, usually you want to compactify to see what happens at the boundary, let's say. And sometimes when you compactify, you find yourself with a cusp or a singular point like this, and your metric degenerates on this point, right? So if your metric degenerates, you find yourself with a singular differential, partial differential operator here. And this is also a very, let's say, studied problem for people which works on the elliptic differential partial differential equations. So now I'm going to define more or less precisely my object. So what's a linear differential operator? So in general terms, you consider a manifold, let's say in the real analytic or holomorphic setting, and you have two vector bundles, E and F over M. And now you can define a differential operator between these bundles as a linear map between the sheaf of sections of this bundle. So you have this, it's a morphism of sheaves. So you have the sections of the first bundle, the section of the second bundle, which I write by calligraphic E and calligraphic F, and you have this morphism here. Of course, this is a two general object. So in general, you can classify this morphism in terms of its order. So how do you find the order of a differential operator? You see how it commutes with the multiplication by functions on the structural sheaf. So a differential operator has order 0 if it commutes with the multiplication operator. More precisely, if you have this relation here, where mu of f is simply the map which multiplies a section of the bundle by a function f, right? So if you have this commutativity, you say that the operation is of order 0. And more generally, you say that an operator is of order d if its Lie bracket with the multiplication operator vanishes after d iterations, right? So basic example, so a holomorphic function, you consider a holomorphic function on your manifold, and it defines clearly a differential operator of order 0 between the structural in the structural sheaf, right? Since of course it commutes with all multiplications. In the same way, a vector field defines a differential operator of order 1. Again, considering let's say the trivial sheaf, the trivial vector bundle given by the structural sheaf. In this case, you see that after two commutations with the multiplication, this is just the Leibniz rule, you get 0. So it's a vector fields. It's simply a differential operator of order 1, and more precisely, it's an homogeneous differential operator of order 1, right? So of course, in terms of local presentation, if you fix local coordinates on a point, you see that differential operator is simply written as in this form, where this phi k are just matrices with rank of f columns and rank of e lines. Sorry. And of course, if it's of order d, then you have to make this this sum. Here I'm using the multi-index notation, of course. So this is each term here is a differential operator of is a derivation of order up to d. Okay, so in this talk, I will just consider the case where the ranks of these operators of these bundles are of order 1. So you can imagine that locally, this phi k, these coefficients phi k are simply functions. It's just sections of the structural sheaf. And well, even in this case, you have very, let's say, difficult and interesting results. For instance, you have to ask yourself the question of local resolvability given a function f, g, sorry, you're trying to find an f such that if you have f equals to g. And very important index problems where you have to find more generally the rank of phi and the co-rank of phi. And okay, so a more general question is how you invert this operator. So of course you have this pseudo differential calculus where you try to place yourself in a convenient function class where you can explicitly write the inverse operator, right? So this is very well developed field. So the basic dichotomy is here that you have the versus the global versus the local behavior. But what's going to interest me more is the dichotomy between the generic versus the exceptional phenomena, right? So you can imagine that this operator has a different behavior in some exceptional set, let's say, which we're going to call the singular set, as opposed to its behavior in the generic, let's say, the complement of this exceptional set. So this dichotomy between the singular behavior and the generic behavior is what's going to interest us here. Let's say, let's just basic example. So if we take a function, remember that I said that a function is can be seen as a differential operator for their zero. And in this case, you can look at the level sets of this function f, right? So in this case, let's say the singular set is the set where the levels, the set of, or the levels are not smooth. And it's a singular set of codimension 2. And explicitly, it's given by the set, if your function is reduced, it is given by the set where the differential vanishes. So of course, here we are interested in characterizing this singular set in more general, for higher order differential operators. And then to understand what happens when you are near this singular set, right? So for a vector field, it's let's say more, perhaps not so classical definition, but what happens? An observed vector field is locally rectifiable outside the subset of codimension greater or equal to 2, right? Equal to 1, sorry. So this is simply the flow box theorem, which says that locally, if you are outside the singular set, you can find local coordinates where a vector field is just a constant one. And the singular set is defined as follows: just in local coordinates, you write a vector field, you expand this vector field in terms of the basis of the tangent bundle. And then the singular set is locally given by the vanish of these coefficients, right? Classical thing. But of course, our goal here is to understand what happens near these singular sets, right? So you, in some sense, you can say that locally things are easy to understand on the generic points, but on the singular set, there are much complexity which can appear. In fact, Tom called these points the organizing centers, precisely because it's according to him, this is where the interesting things appear. So the goal is this: so I'd like to have a good description in the vicinity of the singular points. And in fact, there is a very powerful tool which has been developed during several decades to study the behavior near the singular points, which is the so-called normal form theory. But most of the time, this theory is only can only be applied when the singular points are not too degenerate, right? So it's usually works as follows: if this singular point satisfies some non-degeneracy condition in terms of its, let's say, its versality, and so on, you can say many things about its normal form. But we would also go to treat the degenerate case where the normal form theory is not directly applicable, right? So the approach that I'm going to propose here is the approach that in some sense has been used with quite successfully in the case of differential operators of order 0 and 1, which is the so-called resolution and reduction of singularities approach, right? So let's say in very schematically that there are some steps. The first steps define what we understand by the singularity of a differential operator. So for the moment, I've not defined this in the case where the differential operator is of order higher than 2. But of course, we need some notion which will generalize the well-established notions for the case of vector fields and for the case of functions. So of course, the basic requirements that the local behavior should be simple to be defined outside the singular set. Okay. And well, preferably we want the singular set to be something which is of great codimension, or of, let's say, the simple behavior should be the generic one. Okay. Now, the second and the most difficult step, of course, is to prove that there exists a modification. So supposing that you start with a pair given by a manifold and the differential operators, you want to modify your manifold and at the same point, at the same time, modify your operator by a morphism, phi, which I call phi, which such that, so what I understand by a modification, it should be proper and a biolomorphism outside the singular set, right? So by this, I mean that you don't want to modify the points which are already good, the points which are, your behavior is already simple. And then the operator phi prime, it's what we call the strict transform of the original operator. I'm going to define this more precisely in a moment. And finally, we want that all singularities of this. So we are not going to be able to eliminate completely the singularities. We're going to see that there are some phenomena which are persistent. But anyway, the goal is to simplify the singularities in the sense that all the singularities that you're going to find for this final differential operator should be amenable in some sense to the normal form theory, right? So we are going to call the final, this set of simpler singularities, our final models. Okay, so do you have any questions? Okay, so just to give a small list of examples. So if you take the known cases of functions, this is, as I said, it can be seen as zero order differential operators. And this is, of course, this problem, of course, is completely, let's say, clear right now because it's simply a consequence of Hironaka's theorem on resolution of singularities. So in this case, of course, this modification exists. And what Hironaka says is that the final models are simply monomials, in the sense that each function can locally be written in appropriate coordinates as a product of powers of as a monomial, right? So small drawing to illustrate this. So for vector fields, this is a more, let's say, new result and more recent result. And it's already completed in the case where the dimension of the ambient manifold is smaller or equal to 3. And now I have to define more precisely what are the final models that say what we obtain by this resolution of singularities that I just explained it. So the final models are what we call the canonical singularities of a vector field. So how do I define this? So consider again a vector field given by in local coordinates such as this. And the name canonical singularities comes from let's say, a theory which is very fashionable right now in the algebraic geometry called the foliated minimal model program. And it goes as follows. So you consider the local ring at some point P on the singular set. So now here, phi for me, it's a differential operator for the one. And by definition, your differential operator maps the maximal ideal into itself because F1 and Fn are supposed to vanish at P, right? So you have this relation. And by Leibniz rule, this also holds for all powers of the maximal ideal. So the kth power of the maximal ideal is mapped to itself by the derivation. And the linearization, once you have this, the fact that the powers of the maximal ideal are preserved by the derivation, you can consider the linear map given by the linear endomorphism given by what I call the linearization is the map of the quotient of m by m squared into itself. So if you are in a manifold of dimension dimension n, sorry, this is isomorphic to a vector space of dimension n. So this is just, you can see this just as a linear map, just as a linear map of dimension n. Let's say a matrix, n by n matrix in an appropriate, if you fix a basis. And then we say that the derivation or the vector field is log canonical at the point P if this linearization is not nilpotent. So this is what we call log canonical, and then we have a more let's say precise notion of canonical, which I'm not going to give the precise definition here, but if once you have a log canonical singularity, we say that it's canonical if, furthermore, it's not of radial type. That's some.
Daniel, isn't the same as the traditional for this business name of the elementary singularity?
Yeah, that's the same thing. That's the same thing.
So, well, of course, it's none of my business to dictate the terminology to other people, but okay.
Yeah, the idea is that
log canonical is so fashionable right now that you can be easily used with.
Well, there's my collaborator McQuillan, which convinced me to change the name. I used to use the name elementary also, but he says to me that the canonical means something more, let's say, precise in terms of the functionality of the definition, because it's invariant by birational maps. Sorry, but and in some sense, the name elementary is a little bit overcharged. In some sense, it's used for so many things that. But it's the same. Let's say the same definition.
It's not, Daniel. It's not the same, right? It's almost the same.
Yeah, log canonical. Yeah, log canonical is the same as elementary, but canonical is it's elementary plus not of radial type. Sorry, I have to. I'm not going to define it. I mean, but okay. So, in more concrete terms, if you want to,
I just wanted to defend the trademark that was defended by our society communities long time ago. So not everything fashionable should be immediately put on the banner.
Yeah, but don't mind, because in a moment I'm going to change this name again. So let's see if you prefer the last name, because it can also be put in a more general context where you can see this log canonical as a particular case of a notion which is very well established, let's say, in the more general context. So perhaps we can discuss this in the end. So let's say in the more general concrete terms, if you consider the Jacobian matrix, let's say dFi or dxj, is just asking for this matrix to have at least one non-zero eigenvalue, right? So this is very, let's say, now perhaps a more classical definition. So in these two settings, so again, I forgot to say this. So what the result is that if the ambient space is of dimension smaller or equal to 3, then you are able to achieve these final models by a finite number of blowing ups. So a modification of the ambient space is given by a sequence of of sub-elementary operators, which we call blowing ups. So I'm going to explain this with just a drawing. So a blowing up is just a way to separate lines through a point, roughly speaking. So imagine that you're in C2. So you have these lines through 0. And you can see these lines more or less as the action of one-dimensional torus on C2. And then these lines are the orbits of this action. And the blowing up, it's simply, so you see that these orbits, they contain the origin and their closure. And the idea is that you're going to separate these orbits by this algebraic map. And now you see that, let's say, in these orbits, they arrive in different points on this projective space, in this projective line. And this map here gives this, let's say, it's a birational map between some submanifold of P1 times C, which is, let's say, in the real settings, isomorphic to a Mobius band, to C2. So the idea is that to separate lines. And of course, if this origin is some singular point, where some complicated behavior appears, it's more or less natural to imagine that things are going to be simpler when you separate these lines, right? So this is local definition. Just a basic example, if you want to solve, let's say, this function, again, as a differential operator for order 0. So you see that this is not of a monomial type, it's a cusp singularity. So if you do a first blow up, so schematically I draw this blow up as let's say the projective line, which parameterizes the lines through 0. I'm going to write this just as a small circle. So in the first blow up, you still see a singular behavior here, which is not of monomial type. But after 3 blow-ups, if you see what happens locally at each point, you are going to find that this function, or more precisely, its strict transform becomes locally monomial at each point of your new ambient space. So this is say that we have achieved our goal here because we have achieved the local finite models. Okay, so just very schematically, what do you obtain? Let's say just some drawings. If you solve the singularities of a vector field in dimension 2, so you cannot hope to have, let's say, this local monomial behaviors, but you have a very well-established list of topological final models. So these are what we call the phase portraits that you're going to obtain. So this is a very useful result in dimension 2 for vector fields. For example, it can allows you to classify topologically the germs of real analytic vector fields in the plane. Namely, that if you have a real analytic vector field in the plane, if it has at least one orbit which goes to 0, then you can split a neighborhood of 0 in a finite number of sectors, which are either elliptic, parabolic, or hyperbolic. Perhaps you know this result. And again, of course, this result also plays an important role in the solution of Dulac's problem. It's an essential ingredient here. So for vector fields in dimension 3, so this is a more recent result. So I forgot to say that in dimension 2, this is a result which was proved, let's say, in the beginning of the 20th century. And for vector fields in dimension 3, this is more recent. And in fact, what is interesting here is that you have to introduce a more general type of modification of a space, which is called a weighted blow-up, or a quasi-homogeneous blow-up. So a quasi-homogeneous blow-up, I'm going to explain it also with a drawing, is more or less the same thing in the sense that you're going to separate curves which are going through 0, but now these curves are not lines, but they are monomial curves, right? So again, you can imagine this as the orbits of some torus action, and these orbits all contain 0 in their closure, and then we are going to separate these orbits by some algebraic map. So this, let's say, this bold line which appears here, in fact, it's you can see this as the orbit space of your action. And in the case where the weights are not the usual ones, you have the orbit space is the weighted projective space, right? So in general, this generalization of the notion of projective space is defined precisely as this is the orbit space of this kind of action, right? So what's the advantage? That you can take into account with this the quasi-homogeneity of your behavior of singularity. Let's say, if you go back to the same example of your cusp singularity, it can be desingularized with a single weighted blow-up, which is given precisely by taking these monomials, the weights 2 and 3, and you see that after one modification, you achieve the local monomial behavior. One important ingredient here is that when you do these blow-ups in higher dimensions, in general, your ambient space becomes singular. But let's say it's a singularity of a quite mild type, because it's what we call an orbifold singularity. So it's essentially the quotient of a copy of Cn by a finite group. So we usually think that it's a quite controllable type of singular ambient space. Okay,
so, math, small question?
Yes?
So can you think, instead of weighted projective space, can you think of just the projective space and the weights go in the map? Like, instead of having just a projection, you can have a more complicated map that somehow give these weights, or?
Yeah, so what you can do is that I mentioned that when you do this weighted blow up, you find yourself with a singular ambient space, and then what you can do is that you can desingularize this a singular ambient space using, for instance, Hironaka's theorem, right? It would give you a modification mapping, let's say, a smooth ambient space to a new smooth ambient space. But the problem is that remember that you want to simplify, let's say, a vector field which lives in this initial manifold to a vector field which lives in your final manifold. And what happens in dimension 3 or higher is that, in some sense, you have a choice. Either you admit singularities on the ambient space, either you cannot achieve the final models. So in some sense, if you say you use your weighted blowups, let's say you start at a vector field here, you use your weighted blowups, and you end up with an orbifold with log canonical singularities. Then, if you try to desingularize this ambient space by using Hironaka, for instance, let's say pass from an orbifold to a smooth manifold, what you're going to see is that the singularities of the vector fields will become worse, right? So in some sense, it's inevitable, at least in this setting, to allow singularity in the ambient space. This is by this, what I mean is that it's necessary to use weighted blowups here, because you have counter examples which say that either you admit singularities on the ambient space, or you admit non-log singularities for a vector field.
Okay, thank you.
Okay, so let me just make some comments about the basic techniques which are used here. So how do you control that a singularity improves under blow-up? So the main combinatorial object, which is used, let's say, can be used both on the case of functions and in the case of vector fields, is the so-called Newton polyhedron. I imagine that most of you have already heard about it. So let's say it has several applications, but for us, it's used to control the resolution. I'm going to define it here. So perhaps for the case of differential operators, not so standard definition. So again, we fix local coordinates, and we write a differential operator for the D, like this expansion. But if you want to construct the Newton polyhedron, what you have to do is that you have to use the logarithmic basis. So in fact, you're going to re-expand this operator in the way that I've written here in the bottom, by meaning that you're going to expand with monomials x to the power s, multiplied by polynomials on these logarithmic differential operators. So of course, if you are in the presence of a differential operator of order d, these polynomials will be polynomials of degree at most d, okay? But the subtlety here is that these exponents can be also negative, because we are forcing here the appearance of this logarithmic basis. So some of these exponents can be negative. I'm going to show you an example in a moment. So once you have this new logarithmic expansion, this is just more or less a classic construction, you define the support of your operator as the set of integers. So you have this collection of polynomials PS. So the support is a set of n uppos of integers such that the polynomial PS is non-zero, right? Then the Newton polyhedron is just the convex envelope of the support Minkowski sum with the positive quadrant. Sorry. So just a small example here, if you take this function here, so the differential operator of order 0, you see that its support is given by the points 3, 0, and 0, 2. And now I have drawn here that it's Newton polyhedron, is Newton polygon. So an example for a vector field of dimension 2. So as I said, if you force the appearance of this logarithmic basis, you have to allow negative exponents, but I want to convince you that this is a quite natural behavior. So here you see that if you write the d over dx as x d over dx, you have an x minus 1 times y, and this gives you the point minus 1, 0. And the same way, you have the point 2 minus 1, which should appear in your support. And the Newton polygon is now like this, right? Okay, so one last example. Consider the heat equation, so differential operator of order 2. So now to make the things simpler, it's easier to use this binomial notation. So we write the differential operator d over dx square as x minus 2. So this part here, sorry, I cannot see. Yes, this part here is the same thing as d over dx 2, right? But since you divided by 2 factorial, I think. Yes, times 2 factorial. So if you want to, so this shows you that there is a monomial with coordinates minus 2, 0. And in the same way, there is a monomial with coordinates 0, 0, minus 1. So this is the Newton polygon for the heat equation. Of course, one important thing is that this Newton polygon, it depends on the choice of the coordinates, right? So of course, if you change the coordinates, even by a linear map, this will have, of course, you'll modify this Newton polygon. And this is one of the main obstacles when you try to use this construction to the resolution of singularities, because you want to have, let's say, concepts which are intrinsic, which cannot depend on the coordinates that you choose. So what you can read on a Newton polygon, which is independent of the choice of the coordinates. This is one of the important points. So first of all, intuitively, how we measure how singular a germ is by its Newton polygon? So essentially, all the approaches that exist somehow measures the distance between the Newton polygon and the origin, right? So the way that you measure this distance, of course, depends on the approach that's being used. So the classical approach linked to some invariant called the multiplicity, in some sense, it measures this distance by the, I call it the L1 norm. So this, the shape of these balls, in fact, they are diamond-shaped balls, and then this is the multiplicity measure. But in fact, there are other ways that you can measure this distance, and this gives you different ways of measuring how singular your germ is, right? So very, very general. So important things that you have to measure this distance in the logarithmic settings. So I'm going to use this discussion to show to you how we define, in fact, the strict transform. So what's the logarithmic setting? It's the following thing. So the sequence of the blowing ups that you use, each blow up creates an hypersurface in the ambit space, which is in fact a copy of some k-dimensional projective space, right? Remember that I made a small drawing of a projective space of dimension 1, but of course you can generalize this for k-dimensional projective space. And let's say in the sequence of modifications, the union of this projective space, of copies of the projective space is what we call the exceptional divisor. So here's I make a small drawing with the 2 blow-ups. So we have created a first exceptional divisor, and then let's say the second exceptional divisor is just the union of 2 projective space which cross transversally at this point. So at each step, you have, let's see, here you have the differential operator phi0, and then you transform it to phi1 and then to phi2 in the following way. So there's a unique way of transferring phi0 to phi1 and to phi2 and so on in such a way that phi should leave the differential operator, the exceptional divisor invariant in the following sense. If rho equals to 0 is the local equation of the exceptional divisor.
Daniel,
yes.
Phi small and phi capital is the same as was used before, or?
Yes, yes. Yeah, so phi small is the modification and phi capital is the operator, is the differential operator.
No, so it's not clear how you define the conditions of invariance.
So here, I've written here. So you have a differential operator. So it acts on the section of the let's say on functions. So suppose that the equation of your exceptional divisor is whole. It's a reducible equation of your local equation of exceptional divisor. Let's say each reducible component of E is given by a function rho, right? So your operator acts on rho and gives you another function. It acts on rho power k and gives you another function. So what you want is that it maps the ideal generated by the kth power of rho into itself for all k. So this is what I mean by invariance. If you think of the case of a vector field, this simply means that the solution curves of your vector field should be tangent to the exceptional divisor. They should, if a solution curve starts in exceptional on one of these components, it should stay on this component for the whole time.
So it doesn't follow from the fact that the coefficients of your differential operator vanish at the singular point which you treat.
But this is more general, because here, in fact, if you have higher order differential operators, you have to demand this condition for all powers of the defining equation, not only the first one. But for vector fields, it should be sufficient to ask this only for k equals to 1. Okay. And so the second condition, which what they call the strict transform, is that is that in fact phi should not be divisible by rho. What I mean by this is that there exists some power k such that phi applied to the rho to the power k is not mapped on the k plus 1 power of the initial idea. So this is quite technical way to say the following thing is that once you make the first blow up, in some sense you pull back your differential operator, and then what you do is that you factor out the highest power of the equation rho that you can factor out. So this is precisely the second condition. But you don't factor out too much, and this is the first condition, because it should be invariant, but not too much invariant. So these two conditions uniquely define the way that you transform phi0 into phi1, into phi2, and so on. So just let's say a very basic example here. So consider the case of, again, the case of the cusp. So you just make a blow up. As I said, it can be seen locally as a change of coordinates like this one. And then you replace y by x times t. And the idea is that you factor out the highest power of x that you can. So in this case, is x squared. And so the strict transform is given by the term which lies in the parentheses, so it's t squared by minus 1. So in terms of the Newton polygon, the movement is the following one. You see that you have the Newton polygon of the I square minus x to the power 3. And then you make this first transformation, and it gives the polygon which is in the middle. And then the strict transform means that you are going to make a translation to the left, sorry, by 2 units. So this is the division by 2. And again, if you look at the rightmost and the leftmost polygons, and somehow you see that the polygon becomes nearer the origin. So this is more or less a general principle. Okay, so one important application of this final models is that they allow of the Newton polygon, is that it allows to identify, in terms of this combinatorial object, the final models. Let's see how. So for the case of functions, this is very simple, because remember that I said to you that you have this, the case of function, our final models are the monomials, right? But since we are in the logarithmic setting, you can think that a monomial, each function which appears on the monomial, is the equation of one component of the exceptional divisor. So in a certain sense, when you factor out all the possible components of the exceptional divisor, what you find out is a unit, right? So in this logarithmic setting, the final model for a differential operator for the 0 for a function is just a polygon which is a quadrant like this. Well, so where the point here is the origin. So the important thing here is that 0 lies in the Newton polygon of f in this case. So this is the final model for functions. Let's see what happens for vector fields. So the case of vector fields, remember that I said that you have this log canonical situation, and also you have the situation, the generic situation where the vector field is not singular, right? So I've drawn these 2 situations here side by side. So the first one is the situation where the vector field is non-singular at the point. And you see that you have here, if you write if you draw the Newton polygon, you see that there is a point here which is in the negative side. And on the right side, I've drawn the case where you have, let's say, a singular point, but it's log canonical. So in this case, you see that again, in both cases, 0 belongs to the Newton polygon of your vector field, right? And these are the cases which are final models. So the pattern that we let's say we observe in these 2 cases is that the position of let's say, it has something to do with the fact that 0 lies on the Newton polygon or not. Okay, so now, as I said to you, that there is an important dichotomy, which is, let's say, very, very similar to what happens in a field of algebraic geometry called geometric invariant theory, which is the dichotomy between what we call the stable and semi-stable situations. What is this? So, okay, sorry, I'm not going to explain this in the set of geometric invariant theory, but I'm going to define in this way, because this is precisely the notion which appears in geometric invariant theory. So in the general case, now we pass to the case of an arbitrary order differential operator, we're going to see that phi is unstable at the point P if there exists a system of coordinates centered at P such that 0 does not belong to the Newton polygon of phi with respect to the system of coordinates. Okay, so in other words, you can find a system of coordinates such that the Newton polygon of phi on this system of coordinates does not contain 0. Okay. So dually, we say that a point that phi is semi-stable at the point P if for all coordinate systems x1, xt, xn centered at P, 0 belongs to the Newton polygon. Okay, so if you heard about what we call the Hilbert-Manford criteria for the instability or semi-stability of points in geometric invariant, this is precisely the notion that I use there. So, okay. So if you see now, you compare with the notion that we have before, the cases of final models are precisely what we call semi-stable. Okay, so for now, there is a, let's say, there is an unifying concept which works for functions, for vector fields, which says that a final model is a model where the differential operator is semi-stable, right? So this is the good guys. And what we want to eliminate are this one. Okay, so again, you see that if you're not in a, sorry, let me just come back. No, okay. So if you have some unstable point, these are the bad guys for us, because the Newton polygon is far from the origin in some appropriate system of coordinates. So these are the points which we want to get rid of, right? So, okay, so now we have the notion of, let's say, what we call simple, semi-stable and semi-polar, and these are the points, the set of unstable points, which I call unstable points of phi, is a set that we want to get rid of, right? By analogy to the case of vector fields and to the case of functions. Unfortunately, this notion, of course, you see that here there is a, it's based on the let's see, there is a quantifier here, which says that there exists a system of coordinates such that, So it's very hard to work with this definition. And for instance, I'm not able to prove up to now that this set is a closed analytic subset of M, except in the case where the order is smaller or equal to 1, because this is the case of vector field and the case of functions. In both of these cases, these are precisely the notions of monomial, sorry, these are precisely the notion of monomial and log canonical. But for higher order terms, but let's say for higher order differential operators, I'm only able to prove that this unstable set is closed if the dimension of the ambient spaces is more or equal to 2. If I have, I don't know, Patrick, how much time do I have?
Well, in principle, we're almost done. I don't know, how much time do you think you would like to have?
3 minutes.
Oh, yeah, okay, yeah, sure, go ahead.
Just announce the results. So, so of course, just to give a high order example here, you come back again to this heat equation that I mentioned it in a moment. So remember that I've drawn to you the case of, let's say, the Newton polygon of the heat equation, which is this one. So in fact, you see that in this case, the origin lies in the interior of the Newton polygon. And this, of course, is stable by all changes of coordinates. So you cannot find a system of coordinates such that this polygon is pushed away from the origin. So in this case, we see that we are in the presence of a semi-stable germ. Yeah, so just to recall the Cauchy-Kovalevsky theorem. So it is a theorem of existence of local existence of solutions for differential operators. So just in a drawing, the Cauchy-Kovalevsky theorem says can be applied in the case where you are in the differential operator of order D, and you have at least one monomial corresponding to the support, which is on this line here, right? So in some sense, this is a generic situation, but there's let's say a gap between the points where you can apply Cauchy-Kovalevsky and the semi-stable points, because in my case, I also allow the possibility of the presence of points between the 0 and here. And so in some sense, there are new cases which cannot appear for vector field, because in the vector field case, either, let's say you are semi-stable and you can apply normal form theory or a full box theorem, or you are unstable. But here, for differential operators of higher order, have much more possibilities, and there's much more open, let's say, open problems to treat. So just to announce the result, what I was able to prove that in dimension 2, we considered what they call the theorem of elimination of unstable points. So first of all, if you have a differential operator of arbitrary order, non-zero, of course, and living in a compact manifold of dimension 2, then there exists a finite sequence of weighted blowups. So here it modifies the triple given by the manifold, operator, and divisor, such that in the final object that you obtain here, all points of your differential operator are semi-stable. So you completely eliminate the points which are unstable, namely the points where your polygon is too far away from zero. Right? Well, this is just so more, for me, more than the result, what is interesting is the idea which is behind, because I think it's quite new with respect to the usual ideas which has been used through the Newton polygon. Because what I use is a sort of analog of a thing called Kempf unstability theory. So the idea is that now, instead of trying to measure the distance between zero, so the idea is that you're going to make your polygon become nearer and nearer zero as far as possible. So how do you measure this distance? The idea is that you're going to measure this distance using a metric, which is a sort of L2 metric, because it's a metric given by an inner product, a scalar product, right? So once you find this, you fix this metric, what Kempf do is that, let's say in my analog, is a sort of min-max procedure, because you are going to find the coordinates such that the polygon is as far as possible from zero, right? So you find coordinates such that this polygon becomes the farthest possible from zero. And these coordinates, in some sense, are very, very intrinsic. Why? Because once you find these coordinates, I suppose that you have, this is the coordinates which appear here. So you cannot put this point, this is the nearest point, this is the point key, which I've written here. So you cannot put this point farthest away by a local automorphism, by a local changer point. So in this case, you measure this distance, and people from geometric invariant theory call this the speed. And once you have this vector here, the weight is simply given by this a normalization of this vector. So this is the weight that are going to use for the blow up, right? And well, the difficult part is to show that once you blow up with the weight given in such an intrinsic way, this speed will strictly decrease. So let's say you measure it again after blow up, and it will become smaller. So eventually you are going to achieve your goal. So thank you for your attention.
Thank you very much. Yeah, it sounds like there is more to be said about the procedure.
Yes, I have some more.
Right.
Okay, but
well, right. Well, you know, again, let's see first. Are there any questions for, you know, the setup that we saw today and the result? You might have to unmute yourself before you talk.
Sorry,
Patrick, if I may.
Yes, yeah, go ahead.
Daniel,
yes.
You introduced the object which you describe as the Newton diagram for a differential operator.
Yes.
This notion is clearly local, meaning that you need also to treat the monomial coefficients before the differential operators before. So, in fact, your Newton diagram lives not in the say in the case of two variables in the two-dimensional lattice, but rather in the four-dimensional lattice of powers of x and the derivatives in each x.
Yes.
So I could not really figure out what is the final result. So you claim that by using monomial transformations or quasi-homogeneous monomial transformations, you can simplify this even-dimensional Newton diagram to some form which is which does not contain the origin. So, for instance, let me ask the probably idiotic question. Suppose that your dimension is 1.
Yes.
So you have only one variable, x, and only one derivation, d over dx.
Yes.
Your differential operator is characterized by the Newton diagram on the plane.
No, sorry, Sergey. No, in fact, there's, let's say, there's another notion of a Newton polygon where this is I think we call this Ramis. I don't know the precise name. There's a Newton polygon where you take into account the order of the differential operator, and this is perhaps is what you're mentioning. But in my case, in fact, if you have an ordinary differential operator in one variable, my polygon will be one-dimensional. Okay, so.
Okay, so it's probably a mistake in comprehension. So,
yeah.
Well, I'll write you privately on what I had in mind.
Yeah. So I think it's perhaps one of the one thing that you can find quite strange about this construction is that let's say when you work with differential operators, partial differential operators, one important object is what they call the characteristic variety, which the variety living in the, let's say, in the cotangent bundle given by the monomials in the operators and the functions, right? So this is perhaps this is the, let's say I have two, if you are in
basically this means that your theory is meaningful starting from dimension 2 of the space variables.
Yes. So in some sense, in my construction, you cannot filtrate your operator by the order. So in some sense, the characteristic variety is hidden here. You cannot see it directly because let me just give you again.
No, say Daniel, probably I guess you have something written on this subject. So if you send me a reference, I would try to read it and.
Yeah. So yeah. So, but you see here in the construction, you see that this P of S, these polynomials can have arbitrary order. Let's say up to D.
Well, that's exactly what I said. So you have S as a multi-index and X D over dx, which is also multi-indexed. And so you have an even order lattice Z to n, and your diagram is living there and not in
that's it.
Z to n.
Yeah. So in some sense, it's a sort of a filtration of differential operator, which you let's say you stress more the powers of X and not the powers of the operator. So this is the way that I work.
Okay, so I guess that we can settle our questions between ourselves.
I also have a question. So in your statement for surface seems to be implicit that the set of unstable points is always codimension 2. Is that right?
Yes. No, it can be codimension 1. Not sure it's no,
So,
because
but how do you get rid of them by blowing up?
because once you let's say, suppose that your polygon can be a quadrant, which is let's say at some height, and then at each blow up it decreases like this. Okay, so in fact, once you include, let's say, suppose that you have a line of unstable points. When you blow up, you are going to include this line on your exceptional divisor, right? And then when you include it in the exceptional divisor, you can factor out the power of the equation which defines this exceptional this line, and this gives you your Newton polygon becomes nearer and nearer zero, in fact. So it's a more, yeah.
You are saying that unstable in codimension 1 implies divisibility in your definition.
Yeah, in fact, even for the case of, if you could think of the case of vector fields, usually when we work with vector fields, we suppose that the singularities are of codimension, the set of singularities of codimension 2. But even if you have singularities, codimension 1 singularities, you can get rid of them. By this.
You don't blow up, you just divide. That's my question. So unstable, a differential operator with isolated singularities, the set of unstable points has codimension.
Yeah.
Is that?
Yeah.
Okay,
so,
thank you.
Yeah, any other questions?
I have another question.
Okay, yeah.
Sorry, one question. So, is this collection of coordinates where you have the furthest distance to the origin?
Yeah.
Is this playing an analog role of maximal contact hypersurface, or is it?
No, it's very different, in fact.
Okay.
Because how this no, because in fact it's easy to see that. No, let's see. It's you can see that even in the case of vector fields, you cannot define a maximal contact surface. It's something which is let's say a new phenomenon which appears already in the case of vector fields, is that the theory of maximal contact does not behave well in at least in the approach that I've tried to make. So already the fact that there's a hypersurface which is contained in a stable way all the points which are of higher complexity, in some sense, it's something which does not hold in the case of vector fields. So it's a different approach, but it's very, very similar to this approach which has been proposed by Kempf. So this the idea is that in geometric invariant theory you have this this measure of the instability given by the distance between the polygon and zero. But of course, here he works in a finite dimensional setting. Now I have, and this gives you a sort of stratification. So this is the stratification by the speed, and this is what we call the Hassen-Link stratification. So my goal is to prove that this stratification also holds in the infinite dimensional setting that I'm trying to apply it. So it works in dimension 2, but I'm not sure that it works in the higher dimension.
Okay, because I mean, from what I remember from Kempf's book, paper, like you only need an action on a variety, right? and then you can apply this.
Yeah, but the problem is that is this magic word here, because the Kempf theory is for reductive
Yes,
groups.
okay, yes, you are correct.
And
Yeah.
In our case, we're very far from this. Well, there are some people which have developed perhaps I just give this reference. There's very recent results on the non-reductive geometric invariant theory. And perhaps I can adapt this for my setting, but there's a quite active domain of research about how to apply these tools in the case where your group is not reductive.
Okay, yeah, thank you.
Okay, well, any other questions? I'm guessing that's a no. Well, let's thank the speaker again. Thank you very much.
Okay.
A very nice talk. Just before everybody goes, I'm thinking that we will be organizing seminars like this, not weekly, that's too much, but regularly. If any of you would like to speak, please let me know. All right, that would be nice to know. And also right now, it seems like there are still a lot of questions. People would like to see a bit more of this talk. I don't know if Daniel, you're ready to maybe follow up on this.
Yeah.
What do you think? You would like to?
About the proof, if you want. Let's,
a little bit about the proof, yeah.
Yeah.
I think it was very instructive what you told us so far, and
yeah,
it would be nice to see a little bit how the algorithm works.
Mm-hmm.
So I think we'll probably plan another one, follow up with this one in a couple of weeks or so.
Mm-hmm.
So yeah, that's all I have to say. If you guys would like to talk to each other, we can stay on for a little longer, or eventually I will have to turn it off, I guess. I think we have the time slot for a little bit longer. But yeah, I know it's a little strange. I don't know what to. I'm not a good master of ceremonies, but you might have to unmute yourself if you want to say something. I can only ask you to unmute. I cannot unmute you directly.
So then I have more questions, but this is a little bit unrelated. So like I was checking the Daniel's paper, resolution of singularities of real analytic vector fields in dimension 3. So like, is this the strategy you follow, or is this like what is the difference between this and the strategy? Because in the other one,
it's different.
Yeah, it's a little bit different, but
yeah. In fact, it took me a long time I tried a lot to adapt my, even for the case of vector fields in dimension 4 or higher dimension, I tried very hard to adapt the techniques that I used for this high dimension case, and I realized that they are not. Yes, it's very. Yeah, I did not succeed to adapt them. So my approach was, in fact, motivated by to prove the results for vector fields in higher dimension, right? So I realized that the technique that I was trying to develop did not put any restriction on the order of the differential operator, right? So the idea is that if my approach works for vector fields, it should also work for any order differential operator. So in some sense, I was able to prove that it works for differential operator for the for arbitrary dimension 2, but it's quite different because in some sense, my usual approach is to measure this distance by the L1 norm. As I said, what you do is that you, in some sense, instead of using the distance with respect to some inner product with the norm, you use the L1 norm by saying that you just look at the points which are near the origin as the multiplicity, right? So it's very different. I make some transparencies comparing these two approaches, but by the way, it's also different from the approach that has been recently developed by McQuillan and Marceau in their paper. In some sense, they use an approach which is similar to my original approach in two-dimensional vector fields. And it's not the same. Sorry, I cannot give too much details.
No, I would certainly be happy to see a little bit more how this works.
Is that right, perhaps?
No, but let's do that for another seminar. I think I'm guessing you can easily talk another hour on this, right?
If you want to hear me, yes.
Yeah. Oh, that would be nice. So we'll figure out another time slot in a couple of weeks or so.
Okay.
And I'll do that.
Okay.
All
So
right.
thank you very much.
Thank you for the great talk.
Bye-bye.
And bye-bye.
Thank you.